All right, I'm not going to be official about anything here. We're just going to do a quick and dirty introduction to Gaussian and Gauss-Jordan elimination. This is a way to solve a method to solve systems of equations so that you can get, it's an algorithmic method, really what computer algorithms are based on for solving systems of equations. Of course, the computer algorithms that are based on or that are used to solve systems of equations are more advanced than just Gauss-Jordan elimination. However, the basis for how they're solved is kind of rooted in Gauss-Jordan elimination. Now we'll start with a system of equations, solve this system of equations. And you could go about the old school algebra way of doing this, or you can invent something totally new. And so that's what we're going to do here. First thing I want to let you know, kind of as an aside, so I think I'll scroll to the right here actually to do the aside. First thing I want to note to you is that if you have an equation, let's just say an equation x equals 2. The solution to that equation remains unchanged if you multiply both sides by a number, a non-zero number. Let's say you multiply both sides of this equation by 3. The solution to that equation, to the resulting equation, is the same, right? X equals 2 is still the same solution. So the first thing I want to note, and this is more of a justification than anything else, not a proof, but a note. Solutions to equations remain unchanged when you multiply the equation by a non-zero constant. Obviously, multiplying by 0 means that you would just get 0 equals 0. You wouldn't have variables left over. So you must retain some type of non-zero element in there. So you must be multiplying by a non-zero constant. So that's what we would call our first row operation that we're going to allow ourselves. We're going to allow ourselves to multiply by a non-zero constant because we can do that. So if I scroll back over here to this system of equations, that means that I could take any of those 3 rows, or maybe all of those 3 rows, and multiply them by any number I want, as long as it's not 0. Okay? And the solution to that system will remain unchanged. The second thing I want to note here is that if you take, and again, I'm going to just make up an example here, but if you take a system of equations, suppose that we want a system of equations with the solution 1, 1. I'm just going to make up a system of equations with this as a solution. So the easiest way to do that is just to go ahead and say, make up some coefficients, 3x plus y. So if x was 1 and y was 1, the answer should be 4. And also, you can, let's say, negative x plus y. Let's just go ahead and do that. So again, if x were 1 and y was 1, the answer would be 0. Okay, so we have this system of equations. I just made this up. But what we're going to do is go ahead and add these 2 equations together. I'll call this first one row 1. I'll call this second one row 2. If you add row 1 to row 2, the result here will be a 2x plus 2y equals 4. That's actually, I shouldn't write equals, I'll say implies. So we get 2x plus 2y is equal to 4. And notice, if x were 1 and y were 1, this is still a true statement. In fact, you could take any multiple, you could do this all day long, and take any multiple of these rows and add them to each other. So let's say I want to take 3 times row 1 and subtract 2 times row 2. So if I do that, imagine I take 3 times row 1, so I'll have a 9x. In fact, maybe I should do that. 9x plus 3y is equal to 12. That's 3 times row 1. And negative 2 times row 2 would give me a 2x. And negative 2y is equal to 0. Again, if you check each equation separately and plug in 1, 1 for x and y, you'll see they work out, right? 9 plus 3 is 12, and 2 minus 2 is 0. And if you were to add those 2 equations up even, you would get 11x plus, y is equal to 12. And again, when x is 1 and y is 1, still stays the same. So the punchline here is that any multiple sum or a sum of multiples of rows would still retain the same solution. Let me write that down. So I wrote it this way: solutions remain unchanged when adding multiples, non-zero multiples of a row to another row. And when I say rows here, I'm saying that you have a system of equations, and it might be 5 rows. So you have a first row, a second row, a third row. That system of equations would define a unique, hopefully a unique solution. And so that unique solution would remain unchanged if you add 14 times row 1 to row 2, or 14 times row 1 to 7 row 2. Okay, the solutions would remain unchanged. So that is another row operation. So we have 2 row operations we're allowed to do that would not change the value of the solution to a system of equations. The first one being that we can multiply a row by any non-zero constant we want. Second one is that we can add multiples of rows to other rows. And again, solutions remain unchanged. The last one is more of a trivial statement, often not worth mentioning because it seems so obvious, but it's that you could take 2 rows and just swap them. In other words, I didn't have to write this system of equations here as 3x plus y is equal to 4 and a negative x plus y is equal to 0. I could have written negative x plus y equals 0, and then below that, a 3x plus y is equal to 4. So I got to swap the order of them. And that seems very trivial, but still, those 3 operations define what we would consider to be the row operations, the elementary row operations, in fact, for a system of equations. So let me go ahead and write those in strong form here. So there we have it, the elementary row operations. Multiply any row by a non-zero constant, add multiples of rows to each other, usually non-zero multiples of rows, and then swapping rows. Those are all allowable. The reason why I mention all those before we solve this system of equations, which we could solve this system of equations using old algebra techniques, but we're going to invent a new technique here. I kind of skip Gaussian elimination and just go right for Gauss-Jordan elimination. However, I'll mention where Gaussian elimination and Gauss-Jordan elimination differ. Okay, and by the way, if you take a linear algebra course, you'll get more theory in that course than what I'm giving you today. But this is just a quick and dirty lecture. So this is just to get us into the frame of mind of being able to solve systems of equations using Gauss-Jordan or Gaussian elimination. One last thing, we're going to create a little definition here. And the definition that we're going to create is going to just allow us to really have the same language for this entire discussion. So let me go ahead and write a definition here. Okay, so I scrawled this out here real quickly. Row echelon form. So this is the form of a matrix that we're going to try to get into. And the way we're going to get into this form is via a method called Gaussian elimination. And then we're going to create a more elegant form, which we would get to using Gauss-Jordan elimination. So row echelon form is a form we're going to get to using Gaussian elimination. And then we'll have another form, reduced row echelon form, that we will arrive at using Gauss-Jordan. But the row echelon form is a matrix such that the first element, first non-zero element in a row is 1. And then every row thereafter also starts with 1s, and those 1s appear to the right of the ones that are listed above. And finally, if there are any 0 rows, they're all listed at the bottom. And I'll give you some examples, just quick scrawled out examples here that you could see. So for example, that pen is not really very thick, but here's a matrix, and I'll explain what augmented means in a little bit, but here's a matrix that's in row echelon form. So 1, 0, 0, 8, 0, 1, 2, 3, 0, 0, 1, 5. So this, and notice I have that vertical bar. That vertical bar is an augmentation. Don't worry too much about that right now. The most important piece is to note that this is actually in row echelon form. Each row has the first non-zero element being a 1. So you can see each row. Here we go. The first element in the first row is a 1. the first non-zero element. The first non-zero element in the second row is a 1, and the first non-zero element in the third row is a 1. On top of that, if I start at the first row here, I notice, okay, it starts with a 1, but if I go down to the second row, the first non-zero element in the second row, not only is it a 1, but that 1 actually appears to the right of the 1 that was listed above it. Okay. Same thing when you go from the second to the third row, the first non-zero element is actually to the right of the first non-zero element in the row above. Finally, this example doesn't contain it, but if you had a row of all zeros, you'd put that down below. So let me go ahead and just throw one last example out here. Example. Again, but this time I'm going to create kind of a larger example. Let's suppose that we had something like 0, 1, 2, 0, 1, and a -3. 0, 0, 0, 1, 1, 1. 0, 0, 0, 0, 1, 0, and then 0, 0, 0, 0, 0, 0. This is in row echelon form. Again, the first element, the first non-zero element in each row is a 1. Moreover, in each row, the ones that are the first elements appear to the right of the first elements in the row previous. Okay. And finally, the last row there is a 0 row. So all the 0 rows are listed down at the very bottom. We could do this just by swapping rows because that is a row operation we're allowed to do. We're allowed to swap rows. So this is a good example of a matrix that's been put in row echelon form where we're skipping elements, right? You see that it doesn't go right down the main diagonal like this guy does. It actually kind of staggers quite a bit at certain points, and that's perfectly fine. That's still row echelon form. If you happen to have a matrix that does that, however, it screams out certain conditions or certain issues with the solution. Not terrible, it's just certain issues. Notice that there are still numbers in this matrix. So if you look at the first matrix here, this guy, okay, if you look at that first matrix, there's that 2 that's in that square matrix to the left of the augmentation. So I'll highlight it here. You still have this 2, this guy right here in there. Also, in the second matrix, you have this 1 and this 1. I'm not going to highlight the other 2, but I'm at least going to highlight the 1 and the 1. And the reason why I'm not highlighting the 2 is because that is not important for us. What is important is wherever we have a 1, whatever column you have a lead 1, you want to make sure that every other element in that column, if you're going to put it in reduced row echelon form, every other element in that column must be 0. So let me go ahead and write that down, and then I'll discuss it again. So reduced row echelon form is a matrix in row echelon form. So these matrices, again, right here, row echelon form, lead coefficients or lead terms are all 1s. All 0 rows are down below, and those lead 1s occur to the right of the lead 1s in the rows before. Okay. However, there's a little extra condition. Any column with a leading 1 has 0s everywhere else. So if I scroll up just a little bit, I'm going to copy these so I can have some extra room here. So I'll grab these guys right here. We're going to go ahead and copy them. And I'll paste them down below. There we go. All right, so these are not in reduced row echelon form. However, if we were to magically be able to, and let me just clean this up a little bit, if we were to magically be able to do some mathematics here, to kill off that 2, and maybe in the process of killing off that 2, it could be that we might modify somehow this number that was a 3 there. So it might become, let's just pretend, a -7 or something like that. But notice now this matrix in the first example is now in what we would call reduced row echelon form, where all the lead numbers in each row are ones. They occur to the right of the ones prior, or the rows above, and all zero rows are listed at the bottom, which there are none here. And finally, any column that contains a lead 1 has zeros everywhere else. That is considered to be now in reduced row echelon form. And you could do the same thing, by the way, with this second matrix. You could just zero those out. It's not that you can magically just zero those out, but if we could do some type of mathematics that would zero that out, and it might change the numbers on everywhere else, but we're just going to, for the moment, pretend it doesn't. Then this would also be in reduced row echelon form. Right. So the goal here is to figure out how do you get matrices into row echelon and reduced row echelon form. Row echelon form, not so much. That row echelon form that you see here, not that important. It allows for back substitution when you solve, but reduced row echelon form is super important. We'll see why in a moment. So let me go ahead and start up an example and talk about how to get into reduced row echelon form. So here's the example that I started the entire video with. And what we're going to do is first place these coefficients into a matrix. So the coefficients of the variables go into what we call a coefficient matrix. And so let's go ahead and see what that means. I'm going to say let A, I should write let here, let A be the coefficient matrix 5, -2, 4, 1, 1, 1, and 4, -3, 3. And you should be able to see that each of these corresponds to the coefficients of x, y, and z in each of those rows of that system of equations. We're also going to go ahead and let x, the vector x, or if you want to call it a column matrix x, be x, y, z. And I'll show you why in a moment. And finally, we're going to let the column matrix, or the vector, b equal 10, 9, 1. Now, if you look at these pieces are all the pieces that are in the system of equations here. So you have all the lead coefficients, or all the coefficients of your variables in the matrix A. You have all your variables in the matrix X, or the column vector X. And you have all of your right-hand side elements, or constants, in a column vector B. So let's see how we can kind of glue these together. And as we have seen in a previous video with matrix multiplication, if I were to take A and multiply it by X, well, that means I would take the coefficient, we call this a coefficient matrix A, 5, -2, 4, 1, 1, 1, 4, -3, 3, and we multiply it by the column vector x, y, z. If you do that, again, remember, you would imagine picking up this column matrix, tilting it on its side, and putting it right over each of the rows. So you would see the multiplication. You'd multiply element by element and add. And if you did that, that multiplication would result in 5x minus 2y plus 4z, 1x plus 1y plus 1z, and finally 4x minus 3y plus 3z. And we happen to know from the initial system of equations here that each of those equations, or each of those statements, I suppose you should say, should equal 10, 9, and 1 respectively. So these should be equal to each 10, 9, and 1. But we have an easier way of writing it. We can write that as a column vector 10, 9, 1. And this shows us, which is equal to b, this shows us that really, rather than writing our systems of equations as this chunk in the middle, we could forego that, call that the coefficients of the variables a matrix A, call the column vector of the variables the matrix X, and call the column vector of the constants the matrix B, and you can easily just rewrite this as AX equals B. Well, now there's even a better way of writing this. So you can rewrite this without even an equal sign. And the way we do this, we use an augmented matrix. And the augmented matrix takes the coefficient matrix, the 5, the -2, the 4, the 1, the 1, the 1, and the 4, -3, 3. And instead of stopping it right there, we'll put a vertical bar. The vertical bar is an augmentation bar. It allows us to basically say there's an equal sign there, and there are variables that will lay on top of the 5, the -2, the 4. The variables might be x1, x2, x3. They might be x, y, z. They may be a, b, c. We don't know. But the fact is, there are variables that are going to lay on top of each of those columns. And then to the right of the augmentation bar, we place the constants 10, 9, and 1. This is an augmented matrix. All right, so let me just, without being super long-winded, let me reiterate one little thing here. Given a system of equations, doesn't matter how large or how small it is, given a system of equations, you can rewrite it in augmented matrix form by taking the coefficients of the variables, vertical bar, and then the constants. That's what you get. This is the augmented matrix. We are going to perform row operations, the elementary row operations that we're allowing ourselves, which is you can multiply any of these rows by any constant you want. You can swap rows, and you can add multiples of rows to each other. We're going to do this until we get down to reduced row echelon form. So let me write that down. I'm going to say that we want, in the long run, RREF, reduced row echelon form. So we want something hopefully that looks like 1, 0, 0 augmented with a number, 0, 1, 0 augmented with a number, and 0, 0, 1 again augmented with some number. The reason why we want that is because, remember, the first column represents x values, the second column represents the y values, the third column represents z's, the coefficients of z's. And so if we were to get into this format, this reduced row echelon format, we would be able to say 1x plus 0y plus 0z, or in other words, x, is equal to some number. The second row would tell us that 0x plus 1y plus no z's is equal to a different number. And finally, 0x plus 0y plus 1z is equal to another number. And so you would get your answer to your system. We would be able to develop an algorithm to get an answer to this system. Now, I'm going to tell you right now, there are a lot of little tricks that you can do along the way. I'm not going to teach tricks right now. I'm just going to teach you the brute force method. You can get very savvy with how you do this, but I'm just going to kind of showcase the basic idea. So because we want to get 1 here in the upper left corner, what I'm going to do is either force this guy right here to be a 1, because I can divide or multiply a row by any number I want. I could divide this first row by 5, but you can be a little smart about it, and you can just say, oh, you know what I'm going to do? Instead, I'm going to swap these 2 rows, because you could always swap rows, and that would force that upper left element to be a 1. The way we note this is we say row 1 exchanges with row 2. And so now I'm going to go ahead. I'll make all my elementary row operation notes in red. So when you trade row 1 and row 2, you get 1, 1, 1, 9, 5, -2, 4, 10. And row 3 stayed the same, 4, -3, 3, and 1. by the way, you have a lot of rewriting that you're doing when you're solving matrices like this or systems of equations like this. But just to let you know, it's a good algorithmic method. It's wonderful. So now what I'm going to do is force everything below to be 0. I'm going to force this and this 0. So my goal is to make ones, kill below. Okay, that I don't kill above, I only kill below. Some people teach about making the zeros go above at the same time. I don't, because I think that that's a tragic method. It leads to more computation than necessary. All right, so how are we going to do this? How are we going to kill off that 5 and that 4? Well, we're going to take, since we can take multiples of rows and add them to other rows, we're going to use that 1, and that's the goal here. That's why we made that a 1. We're going to use that 1. Let me highlight the one I'm talking about. I'm going to use this one to kill off all the numbers below it. The way we do that is we're going to take a negative 5. Oops. Sorry about that. Negative 5 times row 1, and we're going to add that to row 2. And I write it this way to become the new row 2. At the same time, I'm just going to, you guys are at a level you can understand this. You could also pause the video if you need to. But I'm going to take a negative 4 times row 1, add that to row 3 to become the new row 3. So I'm going to do both of those operations in one fell swoop. Here we go. Technically speaking, row 1 actually never changed. I'm going to visualize taking negative 5 times row 1 and adding it to row 2 to become my new row 2. But row 1 never actually changes. So here we go. Negative 5 times row 1. I could imagine right here that all of those are being multiplied, including the 9, by the way, are being multiplied by a negative 5. So negative 5 plus 5, that'll give me a 0. Negative 5 minus 2, that'll give me a negative 7. Negative 5 plus 4 gives me a negative 1. And negative 5 times 9 is a negative 45, plus 10 is a negative 35. So there's a lot of little places where you can have arithmetic mistakes here. We also are going to take negative 4 times row 1, add it down. So negative 4 times that 1 would be a negative 4, plus this 4 here would give me 0. Negative 4 times that 1 will give me a negative 4, plus this negative 3 will give me a negative 7. That's kind of nice. Negative 4 times that negative 1 will give me a negative 4, plus that 3 will give me a negative 1. Negative 4 times that 9 is negative 36, plus this 1 gives me a negative 35. Oh, interesting. All right, so notice that, by the way, rows 2 and 3 are identical. I could right now, actually, since they're identical, once you know 2 rows are identical in a matrix like this, you can actually do a little, not trick, but a cleanup, real quick cleanup. I know that I eventually want that lead coefficient, this guy right here. I want this guy to turn into a 1. Again, reading my notes, I want to make 1s and kill everything below. So technically speaking, I could make that a 1 right now, but I'm not going to because these rows are identical. I'm going to go ahead, before I make that into a 1, I'm going to say, you know what? A negative times row 2, add it to row 3, will become the new row 3. The reason why I'm doing that is because if you take a negative row 2, that'll become a positive 7, and if you add it to that negative 7, it'll kill it off. It's a very fast kill. So here we go. I'm just going to write that down. Row 1 has not changed. 1, 1, 1, 9. 0, I technically still have not changed that. So 0, negative 7, negative 1, negative 35. And now, here we go. I'm going to take the opposite of row 2 and add it to row 3. So that'll be a negative 0 plus 0. Well, that's still 0. I'm going to take a negative negative 7, which is 7, plus a negative 7. That's now 0. A negative negative 1, which is 1, plus negative 1 is 0. And a negative negative 35, which is a positive 35, minus 35, that's 0. Notice, by design, I have a row of zeros at the bottom. Now I'm going to go ahead and force this element right here into 1. So I've technically made the first element, the first leftmost upper element into a 1, killed everything below. I'm now going to make this next one in line a 1, or next number in line a 1. So I'm going to divide row 2 by a -7. So -1/7 times row 2 becomes the new row 2. And when you do that, you get the following: 1, 1, 1, 9. Again, I'm not changing anything with row 1. Divide or multiply each of these elements by -1/7. That'll be 0. That'll be 1. -1/7 times -1 is a +1/7. And -1/7 times a -35 is a +5. And you have 0, 0, 0, 0. Now, technically speaking, this is in row echelon form, because all the lead numbers are 1, and those 1s kind of stagger down to the right, and the bottom row is all 0s. Or basically, if there is a 0 row, it's at the bottom. But it is not in reduced row echelon form. To get that done, once I'm done getting into this row echelon form, where we have lead diagonals being 1, lead elements in each row being 1, and all 0s down below, and they stagger. Once I get there, my goal is to make sure in every row that I have a lead 1, or every column that I have a lead 1, that I make sure that the rest of that column has 0s. So that's true in the first column, but the second column here, that guy up there, it needs to be turned into 0. So let me go back to my recipe. I'm going to make 1s and kill below. Once I do that, once done, not down, once done, I quote-unquote kill above. Every time I go for these kill steps, really I kill things using the 1s. So if I look at this matrix now, I'm going to go ahead and use this number 1 to kill this guy up above. So you're always using your highlighted number 1 elements, the yellow highlighted number 1s, to kill above or below. So in this case, I'm going to go ahead and say, well, let's see, how would I use that 1 to kill off that 1? Well, it's a pretty easy statement. I'm going to take the opposite of row 2 and add it to row 1. That'll become my new row 1. That's how I'm going to kill off that element in row 1. So notice in this statement, row 2, the only thing that's changed is row 1. So row 2 and row 3 I'll rewrite. Row 2 is 0, 1, 1/7, 5. Row 3 is 0, 0, 0, 0. Now we're going to go ahead and take the opposite of this second row here, and we're going to add it to row 1. So -0 plus 1 is 1. That should never change. Once you get a 1, it should never change. Again, -1 plus 1, that'll give me 0. -1/7 plus 1 will give me 6/7. And -5 plus 9 will give me a 4. This is now in reduced row echelon form. And this is perfect because now when I go back to my system of equations, remember the system of equations, these were x, y's, and z's. That's what the columns represented. So this tells me that 1x plus 0y plus 6/7 z should equal 4. It also tells me that y plus 1/7 z is equal to 5. And then we don't have another row because the other row is all zeroed out. In other words, that x is equal to 4 minus 6/7 z, and y is equal to 5 minus 1/7 z. That's very traditional. I remember when I was a student, I hated this, but it's very traditional to say, great, okay, so I now know what x and y are. Z can be anything, so we're going to go ahead and I hated this when I was a student, let z equal t. We're parametrizing z. Why didn't we just leave it as z? Well, When I was a student, I could never figure that out. I hated it. I hated the fact that why would we let it be t? Why don't we just say it's z? It's because z is the variable, t is the parameter. Some people will let you get away with it. But anyway, it's not that big of a move here. If you let z be t, then x is equal to 4 minus 6/7 t, and y is equal to 5 minus 1/7 t, and this is the solution. Once I know what t is, which I can let t be any number I want. If t is 0, then x is 4, y is 5, and t is 0. If t is 1, well, then you could do the math, right? But there I have my solution to my system of equations. All right. Let's do one more. And this one more, I'm going to make a big system, and we'll go through and we'll create the system and everything. I just need a drink. Hold on. All right. So in summary, what we're going to do is force ones in the first element of each row, first non-zero element of each row. Use that one to kill everything below in that column. And then once we're done doing that for every row, then we use those ones to start killing above. So let's go ahead and make up an example. And every time I make up an example, bad things can happen, but I'm okay with that. Let's just go ahead and make up a system here. So I'm going to scroll up here. And the way you can make up your own system, and like I said, there are dangers with it because you can end up with some really brutal systems, but you can make up your own solutions. So suppose that you want your system, and let's make up a 4x4. Suppose you want your system to have the answer 1, 0, -2, and 3. Okay, so we have that as our solution. Now you can start making up coefficients for x, y, z, and t. Or maybe I'll be very kind of algorithmic about it, and I'll have x1, x2, x3, x4. So let's suppose that we have x1 minus x2 plus, actually let's make that a 3x1. 3x1 minus x2 plus 2x sub 3 minus x sub 4 is equal to, I'm not going to fill in the right hand side yet. Let's also have negative x1 plus 2x2 plus x3 is equal to. Let's go ahead and have no x1s, and we'll have a 5x2 minus 2x3 minus or plus x4. And finally, let's have another full row in here. Let's just, it doesn't really matter what you choose here. 4x1 minus 3x2 minus 2x3 minus x4. The only thing that you might have to worry about here is that you're somehow copying one of your previous rows, or you're making duplicates. That's the only time that you might end up creating a system with some issues. But let's hope that we didn't do that. All right, so remember, x1, x2, x3, x4 are listed as 1, 0, -2, and 3. So if you plug those in, you get 3 minus 0 minus 4, which is -1, minus 3, which is -4. Okay, and you go through and do this. Okay, so let me just go ahead and say this is -3. This is going to be 4, 7. And this last one is going to be 4, 8, minus 3 is 5. You should always double check your mathematics when you do this, because if you make any simple mistake here, your system's unsolvable, or not for this solution. And that's what I just did. I pressed pause and just double checked. Okay, so now let's write this as an augmented matrix. So here I go. I'm going to write this down below. It is 3, -1, 2, -1, augmented with a -4, -1, 2, 1, 0, augmented with -3, 0, 5, -2, 1, augmented with 7, and finally 4, -3, -2, -1, augmented with 5. All right. Remember, our goal is to force that first element to be a 1 and then use it to kill everything below. You could either divide that very first row by 3, but I see if I do that, I create a bunch of fractions. And that's really your enemy with this, is creating a ton of fractions. So it might be better to go ahead and decide to swap rows 1 and 2. And at the same time, you could really multiply row 2 by a negative. So if I'm going to do that, not very traditional to write it this way, but I'm going to swap rows 1 and row 2, but I'm also going to say I'm going to swap row 1 with a negative row 2. So not only is row 1 going to swap into the row 2 position, but when row 2 goes up to the row 1 position, I'm going to throw a negative in front of it. In other words, swap all the signs on it. Perfectly fine. I can swap rows and I can multiply a row by anything I want. So here's my result. Let me go ahead and write this down. All right. So now that we have the 1 ready to go, highlight that bad boy. I'm going to use that 1 to kill everything below. And what's nice about using that 1 is just because you could say, I'm just going to take the opposite of the number I'm killing off. So if I want to kill off that 3, I'm going to multiply row 1 by negative 3 and add it to row 2. If I want to kill off that 4 at the bottom column, so let me highlight them as I talk about them. If I want to kill off this 3, okay, I will use a negative 3 times row 1 and add it to row 2. If I want to kill off this 4, I'll use a negative 4 times row 1 and add it to row 4. So that is why forcing that to be a 1 first is really nice. All right, so let's go ahead and write this down. Sorry if there was a weird pause there. My phone rang, and so I can't remember what I was talking about. But, okay, so we're going to take a negative 3 row 1 and add it to row 2 to become the new row 2. We're also going to take a negative 4 row 1, add it to row 4 to become the new row 4. Let's go ahead and write that down. And I was actually going to write the whole thing down and then show you the result, but I decided it might be best actually to show you each of the moves here. So I rewrote the first row because technically speaking, we're not really changing the first row and we're not really changing the third either. So I'll write that in 0, 5, negative 2, 1, and 7. So if I take a negative 3 times this first row, if you just visualize it and add it to the second row, that'll be a negative 3 plus 3, which is 0. And if, in fact, maybe I'll write the stuff that's changed in blue. 0. Let's see, a negative 3 times a negative 2 is 6, plus a negative 1 is 5. Negative 3 times negative 1 is a 3, plus 2 is 5. That's going to be convenient. Negative 3 times is 0, still 0, plus a negative 1 is a negative 1. And negative 3 times 3 is negative 9, plus a negative 4 is a negative 13. Do the same thing, row 1, I'm going to multiply by a negative 4 and add it to row 4. So that'll be a negative 4 plus 4, which is a 0. It'll be a negative 4 times negative 2, which is a positive 8, plus a negative 3 is a positive 5. Oof, this does not look good, actually. Maybe I made a linear combination of one row out of another. We'll find out in a moment. Negative 4 times a negative 1 is a 4, plus a negative 2 is a 2. Well, that's not too terrible, I think. Negative 4 times... Wait, no, that's not right. Yeah, that is right. Negative 4 times 0 is 0, plus a negative 1 is a negative 1. And negative 4 times 3 is a negative 12, plus 5 is a negative 7. There is something wrong I can immediately see here. Hold on a second. Negative 4 is a positive 8 minus this. Okay, and negative... Well, it looks like this is a dangerous matrix, but let's just see what happens. All right, so we get to this point. Now our next goal is to force this next lead diagonal element to be a 1. Now, again, this happens to be just the way it worked out. It happens to be that it could easily be used to kill off the 5s down below. Normally, That is not the case. And so what I'm going to do is still kind of go along my merry little way here and force this to be a 1, even though really anybody who's watching this video who knows anything about matrices is going to say, no, you don't want to do that because you can easily kill off those 5s down below. You actually could. I suppose I could just do that. We're going to, instead of forcing that to be a 1 initially, I'm going to use the fact that it's already easy to kill off those 5s down below by using this in its current form as a 5. It's not often you can do that, but sometimes you can. So sometimes you can go off the script a little bit to kill things below. So in this case, I'm going to go ahead and say, well, a negative row 2, add it to row 3 will become the new row 3. And a negative row 2, add it to row 4 will become the new row 4. So let's go ahead and rewrite this a little bit. So remember, the first row I'm not touching, so I'm just rewriting that in. There's a lot of rewriting, as I've said, with matrices. Technically speaking, the second row I'm not rewriting yet either. I'm just going to leave it like this so that I can fiddle with it a little bit later. We've already forced this lead diagonal to be a 1. I haven't forced the next lead element to be a 1 yet, so I won't highlight it. But anyway, opposite of row 2 and add it to row 3. Let's do that one. Opposite of 0, add it to 0 is still a 0. Wait, am I in the right pen color? No, I'm not. Let me get to the right pen color here. Opposite of this 5, add it to the 5 down below it, it becomes a 0. Opposite of this 5, add it to the negative 2 down below, and you get a negative 7. Opposite of this negative 1, which is a positive 1, add it to the 1 below, and it becomes a 2. Opposite of that negative 13, which is a 13, add it to that 7, it'll become a 20. Okay. And now, opposite row 2, add it to row 4. So negative 0 plus 0 is 0. Negative 5 plus 5 is 0. Negative 5 plus 2 is negative 3. Negative times negative 1 is a positive 1. Plus a negative 1 is 0. Well, that's kind of interesting. And then a negative 13, which is a positive 13, plus a negative 7 is going to be a 6. All right. It looked dangerous to begin with initially, but actually it doesn't look so bad now. All right, so what I'm going to do at this point is now, even though I kind of skipped a little, I went off script a little bit, I'm going to try to force that 5 to be a 1. And the way I'm going to do this is just go ahead and multiply row 2 by a 1/5. So 1/5 row 2 becomes the new row 2. And that's just a quick rewrite. Some people just erase their row 2, which I probably would have done, but I'm lecturing on this, sort of. So I'm just going to rewrite it. Again, I'll just say 1/5 times this entire row. That's going to be 1/5 times 0 is 0. 1/5 times 5 is 5. 1/5 times 5, I'm sorry, 1/5 times 5 is 1, and 1/5 times 5 is 1. 1/5 times a negative 1 is a negative 1/5. And 1/5 times a negative 13 is negative 13/5. Everything else is staying the same. So 0, 0, negative 7, 2, 20, and 0, 0, negative 3, 0, 6. All right. Now my next, let me highlight my ones still. So lead 1, zeros down below. We're good. So far, we're really good, actually. So my next goal is to make the next diagonal a 1. And the way I'm going to do this, actually, is I'm going to take advantage of the fact that this already is a 0 there. And if I see that, that's kind of nice. I know I'm going to eventually want only that third row to be a 0, 0, 1, 0 something. So what I'm going to do is swap rows 3 and 4. And at the same time, so row 3 swaps with row 4. But at the same time, I'm also going to divide row 4 by a negative 1/3, or in other words, divide by negative 3, or in other words, multiply by negative 1/3. The reason why I'm doing that is so that I can just force that negative 3 to turn into a 1. So here we go. Again, let me scroll up a little bit. Row 1 hasn't changed. 1, negative 2, negative 1, 0, augmented with 3. Row 2 is not being touched. 0, 1, 1, negative 1/5, negative 13/5. We are now going to drag row 4 into the row 3 slot, 0, 0, but we're multiplying each of those numbers by a negative 1/3. So this will be a 1. This will still be a 0. And then negative 1/3 times 6 is a negative 2. And again, we swap that with row 3. So row 3, I'll write down below 0, 0, negative 7, 2, and 20. And notice that we are really close. Actually, we have almost a nice row echelon form. 1, all the 1s are starting to form nicely in the diagonals. We have to use this newest 1 in this diagonal to kill the element below. So what I'm going to do is take 7 times, let me write this down, 7 times row 3 and add it to row 4 to become the new row 4. So again, I'm actually going to save myself a little bit of time, and I'm just going to copy this. If you could do this on a piece of paper, that'd be awesome, right? So I copy that, paste it here. Okay. And again, we're taking 7 times row 3 and adding it to row 4. So let me just go ahead and erase row 4 just completely so that we can see what happens. So 7 times row 3, that'll be 7 times 0 plus 0 is still 0. 7 times 0 plus 0 is still 0. 7 times 1 is 7 plus a negative 7 is 0. 7 times 0 plus 2 is 2. 7 times a negative 2 is a negative 14. Plus 20 is 6. And we are almost done. I'm going to go ahead and force that 2 to be a 1 now by dividing or multiplying the 4th row by 1/2. And this one I'm going to do a little cheat here. So 1/2 times row 4 is the new row 4. And often, I'm just going to show you what happens when people get bored with rewriting matrices all the time. You know that 1/2 of anything in that row 4 is going to be 0 if the number is 0. So we don't have to worry about those. And 1/2 of that too, it's often easier just to kind of cross it and say it's a 1 and cross this, it's a 3. So there you go. And since I can do that, we'll now go ahead and just erase those and call this a 1 and a 3. And now you can see that I have this actually in row echelon form. So to repeat, scrolling all the way up through all of our work here. Geez, it's a lot of work. Where's my note? A note somewhere. Oh, here it is. We forced the 1s and have used 1s to kill everything below. Now we're at the bottom row. So now we're going to use our 1s to kill above. And you could do this actually in any order, but I have a habit at this point of starting where I just ended at this 1 that I just created, and I'm going to use that 1 to kill everything above. Luckily, there's not much to kill above. And then once I'm done there, I'll use this 1 to kill everything above. And once I'm done there, I'll use this 1 to kill everything above. All right. Seems like a lot, but it's actually not. It's not so bad. So here we go. Really, with this 4th row here, or 4th column, sorry, the only thing that's non-zero in that column other than the 1 is that negative 1/5. So what I'm going to do is, first of all, wrangle this up and move it up above because that's in the wrong spot, is I'm going to go ahead and say, all right, I'm going to take a 1/5 times row 4 and add it to row 2 to become the new row 2. There is a reason why starting with the fourth column and working your way back up and backwards like this is better. So if you follow my method, you're guaranteed to use fewer computations. Okay, so 1/5 times row 4 will kill off that negative 1/5. So let's go ahead and do this. The only thing that's actually changing here is row 2. So I'm going to go ahead and rewrite, and I'm rewriting this because my previous matrix there is ugly. So I'm going to rewrite the whole matrix, 1, -2, -1, I can't see the next piece, 0, 3. Row 2 I'm not going to write because that's going to be new. Row 3 is 0, 0, 1, 0, -2. And row 4 is 0, 0, 0, 1, 3. Again, I'm going to highlight my diagonal. Okay. And here we go. Going to the matrix here, I'm going to take 1/5 of row 4 here and add it to row 2. 1/5 is 0 plus 0 is still 0. 1/5 of 0 plus 1 is still 1. 1/5 of 0 is still 0 plus 1 is 1. 1/5 of 1 plus -1/5 is now 0. And 1/5 of 3 plus is 1/5 of 3 is 3/5 minus 13/5 is a -10/5, which is a -2. So that fraction that we wanted to avoid ends up actually disappearing. And by the way, we still have our diagonal of 1s. And now we have zeros up above in that first column. Now I'm going to go ahead and step over, show the step over here, step over, step backward to the previous one and use that to kill everything above. So I'm going to take negative row 3 and add it to row 2, and then I'll take row 3 and add it to row 1. Let me write that down. Negative row 3, add it to row 2 to become the new row 2. And row 3 added to row 1 to become the new row 1. All right, so here we go. I'm not going to copy it. I was going to copy and paste, but you can't copy and paste, so I'll just do this. Row 4 is not changing, so I'm just rewriting it. Row 3 technically is not changing. Let's see, negative row 3 added to row 2. So negative 0 plus 0 is 0. Negative 0 plus 1 is 1. Negative 1 plus 1 is 0. Oh, I should be doing this in a different color. Negative 0 plus 0 is 0. And negative 2, which is 2, plus a -2 is 0. All right, and then row 3 plus row 1. So 0, 0 plus 1 is 1. 0 plus -2 is -2. 1 plus -1 is 0. And 0 plus 0 is 0. And -2 plus 3 is 1. Again, we still have retained our diagonal elements. And the last little bit, step back again. We finished with that column, so we step back here and we use this to kill off that, and we'll be completely done with reduced row echelon form. This is called Gauss-Jordan Elimination. Gauss-Jordan Elimination differs from Gaussian elimination in that Gaussian elimination got us all the way to this form right here where we didn't kill things above. When you go to kill things above, it's called Gauss-Jordan, and I didn't really make a big deal of it when we were doing this method because the fact is Gaussian elimination, which is stopping when you still have numbers above these ones, is worthless. You want to continue forward. So Gauss-Jordan is the way to go. Gauss-Jordan, getting it into this reduced row echelon form is important. Anyhow, positive 2 row 2 added to row 1 will become our final row 1. So here we go. I'm actually just going to write it this way. So 2 times row 2 added to row 1. That'll be 2 times 0 plus 1 is still 1. 2 times 1 plus a -2 is 0. 2 times 0 plus 0 is 0. 2 times 0 plus 0 is 0. Augmented with 2 times 0 plus 1 is 1. And everything else I'm rewriting. 0, 1, 0, 0, 0. 0, 0, 1, 0, negative 2, and finally 0, 0, 0, 1, 3. Okay, so what's so important about this? Well, remember, the first column represented x sub 1, second was x sub 2, x sub 3, and x sub 4. This tells me that 1 x sub 1 is 1, 1 x sub 2 is 0, 1 x sub 3 is a negative 2, and 1 x sub 4 is a positive 3. Or in other words, the solution to our system is 1, 0, negative 2, 3. That took 1 hour. I'm stopping at an hour.